is Intelligent Retrieval Bots. This is Alfredo Nava, Usolana Ramirez, and I'm Angelica Herrera. The purpose of our project is to research the development of autonomous behavioral techniques as applied to navigational and path robots. Examples of autonomous vehicles are the Google driverless car, Stanley, and Maslar City's Pod Car. Both the Google driverless car and Stanley use GPS, cameras, and an assortment of sensors. The Google driverless car successfully navigated through the San Franciscan Lombard Street without the use of a human driver. Stanley was the 2005 winner of the DARPA Grand Challenge. It would scan the Mojave Desert terrain and it would make decisions as to where it was drivable. Another example is Maslar City's Pod Car. Maslar City is designed to be the world's first zero carbon, zero waste, car-free city. And this was accomplished through the use of personal rapid transit, which the Pod Car is a part of. The Pod Car has a pre-programmed route in which it follows. In order to help it navigate, there are magnets embedded in the roadway over which the Pod Car travels on. If the Pod Car misses two of the magnets, it will automatically shut off. Another example of an autonomous vehicle can be found in the Porsche factory. The biggest challenge that the Porsche factory faced was getting the right parts to the right place just in time for assembly. The solution that was found was the Porsche patented driverless transport. These cars travel through the factory, over a bridge, into an elevator, and down into the assembly area, all without a driver. This makes them fully autonomous. They do this all on their own. These parts also use magnets that are embedded into the road, into the pathway. These parts are capable of moving at high speed while carrying heavy loads. And even with these heavy loads, they are capable of avoiding collision. Our robot is modeled after the real-life autonomous vehicles. Once the robot is placed in a maze, it will solve the maze on its own without needing any assistance from us. Also, the robot can be placed at any point within the maze and will work to solve it all on its own. So the maze is not pre-programmed into it. It does not have a direct route to the final destination. What is unique about our project is that there will be two robots working to solve the maze at the same time, which makes collisions possible, but the collisions will be avoided through the use of wireless communication between the two robots. Also, if there is a fault in the robot's communication, this will also be prevented. And while the robots are going through the maze, there will be continuous common path comparison. This will be accomplished even with limited resources. Unlike the pod cars, as I mentioned earlier, these robots do not have their direct route programmed into them, so they are working through the maze on their own. Also, unlike the Google driverless car and the Stanley, they do not use cameras, GPS, or fancy sensors like laser sensors. Now I'll hand it off to Alfredo.
I want to talk about our maze solving algorithms. The most popular one is just wall following. Basically, the robot will stick to it'll give preference to one side of the maze, and if it always keeps following, per se, the left side, it will eventually solve the maze if it does not have any loops. The data structure to store for path optimization will be an array. We simply store the choices that it takes throughout the maze, and then we optimize the path at the very end of the simulation. Another possible algorithm and data structure will be representing the map of the maze with binary trees. We will use these such as the junctions will be nodes, and then we will delete leaves by themselves as U-turns, basically. They will be detected as that, and that's how we would optimize it. This could be possibly used to solve mazes with loops. Here are the 8 possibilities that we will have within our maze. These 2 right here are basically insignificant turns. They will not be recorded for the best path optimization. We don't need to take account for those. These 2 and these 2 down here are the only 4 relevant choices that we need to record. And these are obviously, this is a U-turn, so basically this means to delete the next and the previous and replace it with a different one. And this just marks the end of the maze. This is a state diagram of our maze and path optimization algorithm. First, the robot will start. It will initialize our sensors. It will immediately go into a following line method. When it is in that, all it does is just follow a line until it detects a junction. Then it will go into a junction analysis to try to determine what type of junction it is. It will decide which direction to turn when it knows what junction it is. And if it is an unimportant turn, like I mentioned before, we do not need to save it, so we'll go back to following the line. Otherwise, if it is a significant turn, then we save the path. And if the maze is finished, we start optimizing the path. If not, we go back to following the line. Once we optimize the path, and that's the end of the simulation, we will transmit the data to the second robot, and it'll go to the end of the path immediately. This is sort of an animation for everyone to visualize how the robots do not need to start at the same position, and we will do them with different algorithms. This one will do the always right, and we'll do the always left rule. And we will do this because there will be no point in having both of them go the same algorithm. That way one of them gets to the end of the maze faster no matter what. Once the second robot down up here gets to the end of the maze, it'll optimize the path and send all of the data to the robot up here. It'll tell it that this right here, this purple path, is a common path between them. This blue robot will continue to navigate the maze, and then finally, it detects a common path with these 7 junctions right here. When it detects it, then it knows where to go. And so it follows the path right there. Then at the very end, the second robot tells the first robot to go back out the shortest path. Now this is an assumption we're making because most likely the robot that finishes first will also have the shortest exit path. So then this is the exit path that both of the robots will take. And simulation is done completely autonomously without having to adjust, calibrate the robots or anything like that. Another test case will be an error. We will purposely cause an error in the transmission on the robot that starts down here. And so what will happen is whether there's an error in transmission of the common path, or there's an error in transmission of when it actually detects a common path and then it's trying to navigate to the end. When it gets to this part right here, it will not have valid data. So this is following always left. So right here we'll take a left turn and instead take the longest path right place. Test case 3 will just be a different maze to prove the concept, so everybody can see that it's not a pre-programmed maze, and it will purposely add more collision scenarios. That way the concept of the error detection can improve. Capabilities of the robot as far as error detection goes is in maze data transmission we can have 2 errors. Either the common path transmission where the data is corrupt and they never detect a common path, so they will keep traversing the maze and it'll still assume it's a maze solving algorithm. So it'll solve the maze whether the common path is found or not. It doesn't matter. And there's also where it actually detects a common path, but it gets to a junction and it says turn left, but there's no left turn. So it'll detect that you cannot turn left, so then it'll discard that data and continue traversing the maze. Another thing we're accounting for is collision. So basically the robots will avoid each other with 3 sensors that we will mount on them. If there is corrupt data transmission as far as collision goes, both of the robots will verify that the collision situation matches. That way they can verify that they are both going to take the appropriate action. And this is the reason why, because there's 4 types of collisions. There's head-on, front-to-back, junction, and dead end. Both of the robots need to agree that they are in one of these 4 scenarios, otherwise they will not know how to react to this. Head-on collision is simply solved by giving priority, giving a weight to one of the two robots, and we would say that robot 1 has priority over robot 2. So robot 2 will retreat to the nearest junction and let robot 1 pass, and then robot 2 will exit and keep going on the original path. Front to back will simply make it where only one robot is detecting the other one. Robot 1 will stop for a second, let robot 2 advance, and once it's out of its line of sight, it'll keep going. Junction collision is when a robot is coming out of a dead end and this one's passing by right here. We'll just make that robot 2 stops and then lets robot 1 pass, and then it'll come out. Dead end is different because both of the robots are already inside of a path, and it is a dead end. So this robot will communicate with this one will tell this one that there's no way out of this. And this one will go back out, delete this out of its path, so it won't take this into its best path optimization calculation. And this one will exit out and continue on its path. And I'll hand it over to Luis.
Our chosen design is a tank robot. It has a built-in Arduino microcontroller, and it's this little thing right here. We will actually have two of these solving the maze. What's good about this is that it has ample space to mount my sensors, and it has an integrated motor controller. One thing though, since it's a track robot, it's going to be slow, but this robot is suitable for our project. Here's a robot block diagram. As you can see here, we have a reflectance sensor array. This will be used to detect the lines in the maze so the robot doesn't get off track. And then we have a digital distance sensor, and this will be used for collision detection. For wireless communication, we will be using the XP S2 wire antenna module. And the whole system will be powered by a 5-volt power source. And this is the Arduino microcontroller. What's good about this is that it has 8 analog I/O pins here, and it has 13 I/O pins here. Also, it has a USB, a built-in USB connection for fast programming and to increase our testing purposes. These are twin motors. They have a normal operating range of 1.5 volts to 3 volts. They can be ramped up to 6 volts, but if we do this for faster movement of the robot, it would decrease the lifetime of these motors. We might have to get new ones. This is a reflectance sensor array. This is what will be used for detecting the lines of the maze. The microcontroller will actually probe each individual sensor and get the value if it's detecting a line or if it's not detecting a line. And it will send it to the microcontroller via an analog voltage output. This analog voltage output will be used to tell the microcontroller if the sensor is detecting a turn, an intersection, or if the maze has been solved. And the digital system sensors, they will be, each robot will have 3 mounted at the very front, and these will be used specifically for collision detection. And the detection range is from 2 centimeters to 10 centimeters. And it will detect the robot via triangulation, so it will emit a beam of light and a reflected light, and depending on the point of reflection, the sensor will tell the microcontroller how close the other robot is to it. And for wireless communications, we are using the XP Series 2 wire antenna modules. These are a key component of our project because these allow our 2 robots to cooperate and send information wirelessly to each other. Our final program will actually have layers to tell the microcontrollers whether collision information is being sent or maze solve information is being sent. And while data is being transmitted, the 2 robots will not move, as you saw in the video that Alfredo showed you. Here's a diagram of possible collision event. As you can see, this robot has gone into the detection range of this sensor right here, and that would be within 10 centimeters. What would happen is that sensor will send the data to the microcontroller. The microcontroller will send the stop information. The 2 robots will stop moving, and the robot with a higher priority will move out of the other robot's range and will keep moving forward. If this was a dead end and this one had higher priority, this will keep moving this way and this will stay fine. And another problem that we could have encountered is that we could create a maze that has 2 parallel paths. If the sensors are mounted too widely, it might detect the other robot while it's traveling in a similar parallel fashion. So what we decided to do is mount the sensors narrowly to eliminate the parallel collision event. And it's a parts toss. Two things that I wanted to point out here is by choosing the reflecting sensor array versus separate light sensors, we saved nearly $200 because other sensors in the market are typically around $15 as well, but this one includes it's a single package. And digital distance sensor, since we also save nearly $100 on that sensor versus other IR rangefinder sensors that have a much greater range. And the reasons why we chose specific sensors for this project is for the reflecting sensor, we chose this one because it's a single package. It includes 8 individual infrared sensors versus the separate light sensor, which each one will have to be purchased individually, and we will have to mount those individually and align them correctly so that they receive information from the surface of the maze. It doesn't interfere with other sensors. And the reason why we chose the digital assistance sensors versus IR rangefinders or sonars is that the digital distance sensor has a detection range from 2 centimeters to 10 centimeters. And IR rangefinders, they typically have a much greater range from depending from 10 centimeters to 80 centimeters or much greater. And that's one problem with the rangefinder. Another problem is that since the range is more than 10 centimeters and our maze isn't going to be that big, if another robot's traveling within that detection range.
To the second, keep going down. Sorry, right at the beginning of the transmitted part. When it gets to the next one right there, how do you tell it how far to go before to turn left?
Oh, we don't need to. What we'll do is we will tell it the direction. So the robot will analyze the junctions, and then it'll get to this junction. And once it detects a common path, it just keeps going on to the next junction. It is not. We don't store any path length data in the where it gets to the end. So we just tell it, okay, you get to the next turn, and on the next turn, turn left. Get to the next turn, and then turn right. Get to the next turn. That's what we do.
Okay, so it's going to store each junction, and then the command at that junction will be pass this by, go on to the next junction?
Yes.
Okay.
And
It's actually the path.
yes. One problem that we realized towards the very end of this is actually the robots can be confused if there is a mirror path when they get right here. If this path is mirrored this way, and this robot is, let's say that this robot for some reason turned right over here, and it detected these same junctions, it would think that it's over here, but it's over here. So what we'll do is one extra thing that we will store with the path data is we will also tell it what direction the original, for instance, if this is the one sending the data, we will tell it what direction the robot turned when it got to that junction. So at this junction, it'll say, I got to this junction, you turn left, you turn left. So if it says that it's left and it goes right, then it'll know that it's not over here. It'll know it's over here.
Have you noticed if there are going to be any synthesis issues with the sensors you're using in the Arduino board? Are they all digital inputs?
Some of the reflected sensor at the bottom, it takes a line that's analog, but the XB and the distance rangefinder, that one's digital. Those two are digital.
And the delay on the to actually get a full reading, so basically the bottom ones are all analog, so it'll have to pull each one of them. The delay can actually be anywhere from 1 milliseconds to 2.5 milliseconds, depending on how many samples we take to average. Right now we have it taking 4 samples, so it'll average the samples. That way it gets a very accurate.
It's like when you said when it was detection, the digital, since the distance sensor is digital, the reading will be very quick.
Yeah. So it won't conflict with the IR on the bottom.
I have 2 questions. What software did you use to animate your maze reversal?
I used Photoshop, and then I made the animation, and then I used a screenshot, basically a screenshot recorder of it.
That's very nice. Okay, the other question, when you store your data structures in a binary tree, so when you do some backtracking like this, you turn right and then you realize you've got to turn left, so you store that?
No. For the beginning, we will implement wall following, so we will put it in 2 arrays. So one array of the directions taken, and then another array of the top junction that it encountered. Yes, sir?
So this unit that you've built here, have you run this unit on a real physical maze yet, or it's still?
No, this is, we've actually gone a little bit beyond what we're supposed to do this semester. We weren't supposed to even interface it or prototype it, but we will actually, it's already ready. We just haven't gotten the sensors. The pseudocode for the maze solving algorithm is already there. Really, what we explain right now is the simplest part of our project. The most complex part is actually going to be the collision detection and the continuous maze solve, continuous path detection.
And obviously the data types, the wireless communications, that's also going to be a major part of the project.
Yeah, because they have to constantly keep communicating with each other when they detect each other. So, yeah. Okay, well, thank you very much.